you have a partial recording but not the entire recording. So, and given that there's not everybody here, but you should be able to, even if this recording doesn't work, you should be able to just work your way through the slides and through the exercise. And there's references to the Crawley book. So also if sometimes you can't get along or you don't understand all the terms I use because I speak too quickly, in the beginning I've given you a reading list, and that has some handbooks to it as well, so you can always look up some of the references I use there. Okay, so we're already at week 7, or lecture 7. So last week we dealt with mediation, and today we're going to talk to you about exploratory factor analysis. And the goals for today, for some reason the screen is also tilted. I'm not sure who knocked the beamer, but it's a little bit tilted. It's not my screen. My screen is nice and straight, but somebody hit the beamer probably. So we'll talk about factor analysis. We'll talk about some ways of visualizing factor analysis. And then for your assignments, so every single time we do things, it's always tied into your assignments. So that's why you all should be here, but yeah. So you should be able to answer exploratory factor analysis and its assumptions for assignment 2. But before we start, who's ever run an exploratory factor analysis? Is this something you covered in your undergraduates? Like, did you do a factor analysis or a principal component analysis? Yeah? Okay. And you remember what the purpose was? So what was the goal of it? Why did you do it? Just because it was a button in SPSS, or? Part of the module. That's, I think, who was teaching it, Matt or?
Oh no, it was not here.
Oh, not here. Okay, so it was part of the module, but you don't recall what it was for, or like why you used it?
It was health related.
It was health related. So exploratory factor analysis usually is the first step before. So you have exploratory. I'll explain in more detail later. You have exploratory and confirmatory factor analysis, and usually we do it when we have lots of items from a questionnaire, for example, and we try to reduce that complexity into a couple of factors or components. So usually you have like lots of things you've measured, and now you want to make sense of that complexity, and that's why you delve into exploratory factor analysis. So we want to study the covariation between a large number of observed variables. Again, think of a questionnaire like a health-based questionnaire, where people have answered lots of questions about their behavior, for example, and then you want to see if we can reduce, let's say you have 20 questions, if you can reduce that to 3 or 4 factors, which explain most of the variation in that set. And there's all sorts of, there was pragmatic reasons to this, because it's just easier to work with fewer items or fewer components than with, let's say, 30 questions or something. And also the idea, as we'll come to this, is that in many psychological theories, the idea is that there's a latent construct or there's something underneath it which captures all this variation. And we'll come to that also when we discuss confirmatory factor analysis and structured equation modeling. So the idea that we want to test is like how many latent factors would account for most of the variations among these observed variables. Again, think of your health questionnaire. You might have 30 questions or something, but they might fall back into depression and anxiety most globally. So they might capture just two latent components or 2 latent structures. And then the second thing we would like to address is which variables of the questionnaire appear to define its factors. And then the question usually is, so you've done this, but they don't come with a nice name to it. And so once you see all those labels going together, all those questions going together, can you name it into something sensible, like depression or anxiety? So usually it's something that emerges from the data. So it's more inductive, so to speak, also. And the idea behind this is that if the observed covariation, again, think of your health questionnaire, is that is explained by 2 factors, for example, like depression and anxiety, then you're able to use those to better, in a further test, to better explain subsequent behavior or subsequent variables. And so basically, it's the goal is to reduce the complexity and increase your understanding. And important to know, this deals with complexity not in terms of number of people, but complexity in terms of number of items, usually in a questionnaire. So I'm not going to talk to you about cluster analysis, but cluster analysis are when you want to group people or group, so to speak, lines of data rather than columns of data, if you think of it that way. Rows rather than columns for cluster analysis. Okay, and so usually it's also the first step. So some of you might find yourself developing skills as part of your internship, or developing new measures, or testing new measures. And usually exploratory factor analysis is the first step. So you have a large question bank, so if, let's say 200 items, and you're going to reduce some of those to see if some of them capture like underlying constructs. And then later on you would do more complex tests, such as confirmatory factor analysis, or some other measures also, like test, retest, reliability. Those are the things you would follow up on with. So it's usually the very first step when you're developing scales in questionnaires. And some of you might end up developing scales either in an HR function, or in a health function, or in a different way. I've already mentioned exploratory versus confirmatory. Occasionally you will have a very clear idea as to how many factors there should be. So suppose you're using a Big 5 questionnaire, then hopefully you would find the Big 5 in there, so there should be 5 factors underneath those questions. So in those cases, confirmatory seems more the route you want to go. As in such a case, one would usually do confirmatory factor analysis. And you might have also heard about this difference. I'm not sure if you did principal component analysis or factor analysis when you were doing these analysis, but they're different. They're different to some degree, and so usually sometimes people use these terms interchangeably and say factor analysis for both, but they are different. They are different things. So principal component analysis is basically, the purpose is to find a linear combination of the variables you have. And the idea is that you've done such a good job that you assume that you have 100% of the variance that you're able to partition amongst all those components. Yeah. So it's basically, it finds a set of orthogonal. Orthogonal means like standing opposite of one another, like just that. If you think of it as a space, it means that one is at one extreme and the other is at the other extreme. So it tries to find things by rotation which are opposite one another. And together they try to explain all the variation in your original data, and there are as many principal components as there are variables, but typically you only care about the first few. So those first few, if we take those things, we'll try and explain as much variance as possible. Now the difference with factor analysis is that it doesn't assume that you have all these this entire variation range. And usually the difference is also if you're interested later on in, for example, using the factor scores, or if you're really interested in using those scores later on, then you would use factor analysis. So the idea is to use correlations between observable variables in terms to really find these underlying factors. So you care more a little bit about those structures you're going to find underneath it, and whether you can use those later on to do this. There's also some differences in tradition. So principal components tend to have been more used by some of the psychologists in intelligence, and some of the other measures have been used by sociologists and some other disciplines. So there are some differences also in history, but I won't bore you with those. So also note that when I say factor here, it's not the same as when we talked about factors as a variable category. So remember that we could have numerical variables. We could also have something like a character or a string, all sorts of things. So when I say factor here, it's factor as in factor analysis, and it's not the same as factor as an attribute of a variable. Yeah. Confusing, but yeah. And although, as I said before, although some people will use these terms interchangeably, principal components and factor analysis are different techniques, and they will give you different solutions. And so today, I will focus mostly on factor analysis, and that's in part because I have a preference, because I think you will hardly ever find a situation where you're such a good measurement person that your variables explain 100% of the variation. So that's why it's my personal preference to speak more of factors than principal components. But if you're a supervisor or somebody else asks you to do principal components, there are very similar commands in R, so you can click on those links, and you can also find out more about the mathematics and how they differ. Again, this is not a maths course. I'm just teaching you statistics and how to use them. So, as with everything, there's assumptions to it. In essence, you can think of factor analysis, because I said it's a linear combination, that should ring some bells that it's like regression. So, which means that similar assumptions of regression apply. So, all the variables should be interval, so they should be continuous. You can have, in this case, you can't have dummy variables, so you can't have gender as a mix or like some other type of 0-1 variable in your factor analysis. And also, as before, you can't have really extreme outliers or things because they will weigh heavily. Sample size. Some people say, as a rule of thumb, you shouldn't do it unless you have more than 200 people. So, but other people say you should have 5 or 10 per variable. And so by variable I mean, so suppose your item had 30, so you're looking at 30 questions, you should have 300 people, between 150 and 300 people. Yeah. But there's some debates also about rules of thumb and whether they're useful. So again, you can read more about those, but some general guidelines. So, but generally not a good idea to attempt it if you have very little data. So if you only have 30 or 40 people, usually you don't want to go down the route of factor analysis. You need multivariate normality. This is less of an issue with exploratory factor analysis. Next week, next week or the week after, I think next week, when we talk about confirmatory factor analysis, there you do require multivariate normality. But here it's sort of useful to check, but it's not that stringent an assumption because it's exploratory more than confirmatory. Relationships are linear, so if you have proposed quadratic or exponential relationships, it's looking for linear combinations between those variables. So if you think that some relationships between those variables are an exponential function or they're quadratic, then it doesn't make much sense to do factor analysis because it will only look at the linear structure. And then there's something known as factorability. So for this to work, so if there's no correlations in those 30 items or those 30 questions you measured, then it's not going to be useful for you to do factor analysis because there's nothing to work with, so to speak. Yeah. So if you have no, if all these items, so if one is measuring your star sign and the other one is measuring your preference for nuts, and there's no relationship between those whatsoever, then it won't work because there's garbage in, garbage out. You can't get magic going. So you can read more on these assumptions by clicking that link. So I'm going to give you an example, then you're going to do it yourself. So the data are from that link. Unfortunately, the original data file that has vanished from the Stanford website. So, but I've uploaded you a version to the Blackboard, so you can also do it yourself. It's personality0.txt. So that's on Blackboard. And there's another example of which uses the same type of data. So we had 240 participants providing self-ratings on a 1 to 9 scale on 32 different variables. And as you can measure, as you can imagine from the title, it has to do with personality traits. So people are scoring is 1 to 9, and here I read the data by read.table because it's a text file. And then with Stargazer, I'm gonna make something for you to look at. Let's see if this opens. Oh, there we go. So Stargazer can also give you the descriptive statistics. So the reason I use Stargazer is just to do this. So you have things like distance, you can see carelessness, hardworking. So all these traits. Then you have the mean, standard deviation, minimum, 25 percentile, 75 percentile, and maximum. So, and you could scroll further down, but there's 32 of those. So that's the data we're working with. So you can see also there's 240 of them, so they're all complete. So we don't have to worry about missings in this case. Okay. So, first the issues for the assumptions, like measurement and sample sizes. So we have 240, so that's if you take this over 200 rule, that's sort of okay. If you need 10 per variable, then we're slightly under, but it's not too bad. So the other issue is measurement, so it has to be continuous. So it's 1 to 9. So you could say that's not really continuous, but it's better than 1 to 7 or 1 to 5. So And many people in psychology would attempt factor analysis with a 1 to 7 type of variable, saying that it's as close as continuous as we're going to get. So I'm not too bothered about the 1 to 9 or the sample size. Multivariate for normality. You might remember that we've done that. We've done that for the MANOVA, and we've done that for some other things as well. So we can do that via the MVN package. Then we get these type of things, and you can see also that this is going horribly wrong because there's skewness and kurtosis, and so it's not upheld. So we don't have multivariate normality in this data set. But because it's exploratory, so you can also see all the nodes here for all these individual tests if you scroll all the way down. So, but we're going to soldier on because it's exploratory, and we're not too bothered about this for now. We can also look at it this way. So we can ask the MVN package to make a plot for us, and ideally it should be all on this line. And the reason it's not giving this is because it's really veering off on that end. Yeah. So if it's perfect, then everything will be close to the line, and it would sort of swivel. So the variation at least would be sort of random. But you can see it's a little bit off here, and then it's really going off there. And that's why these significance tests are these multivariate normality tests are not upheld, and we don't have multivariate normality. Linearity. So are the relationships linear? You can do pairwise scatter plot. So most of the things, again, you check visually. I think plots are usually the best way to check what's going on with your data. So I've done just an example. So I use ggplot. I use a package called ggLE, and then I do ggpairs, and that creates these pairwise plots. So what it does, it gives you a distribution, gives you the correlation, and gives you a distribution here as well of these points in a scatter plot. Yeah. So you can do that for all 30, but then it's going to be way too big to plot. So just some examples. We will just assume for now that linearity will do, and that most of these relationships will be linear, and there might be some which are curvilinear, but for now we're only interested in linear relationships between those variables. But if you wanted to do it further, you can use ggpairs and then subsets. So these, as you remember, this refers to the columns, the second bit. Now the last thing was factorability. So this basically means there has to be some type of association between those things, and so we can test that with Bartlett's test for homogeneity variance. So in this case, we want it to be violated because that means there is associations in these sets. So in this case, this is a test, whereas for ANOVA regression, you wouldn't want it to be significant. In this case, you want it to be significant because it means we've got stuff to work with and stuff to combine. Yeah. So in this case, we do Bartlett.test for the entire data, and we get a highly significant test. So that's good, and we want that to be significant because it shows that there's significant associations with. So you would write this up like Bartlett's test for sphericity was significant, suggesting that factor analysis is appropriate, and then you would use the chi-square, the value, and the p-value. Oh, I forgot to italicize this. This should also be italicized. Sorry. So that's an APA style write-up, but I'll make sure I'll fix the italicization for that. Another test which is usually used for factorability is known as the Kaiser-Meyer-Olkin factor adequacy test, the KMO-test. So if you ever play Scrabble, I'm not sure it would hold, but Kaiser-Meyer-Olkin factor adequacy test. So that's a tongue twister. And so this score will range from 0 to 1. And ideally, all of them should be above 0.5. So in this case, for all 30 items, you'll get some type of measure. So you'll get, so we use the psych package. Then it's just the code KMO, and just you have to make sure. So in this case, this works because we don't have any other junk in our data frame. We only have all the variables in there which we're going to analyze. Otherwise, you would make a subset. So it only has all the items that we're going to analyze. Now we get this output. It gives you the overall measure for adequacy, which is 0.84. That's basically just some average. And then for each single item, it gives you the factorability of that item, and you want none of them to be below 0.5, according to Kaiser. So you can see All of them are looking quite good. We have a couple of lower ones at 0.78, but all of them are still far away from 0.5. And then you have some lovely terms to describe it. So if you have items, they're unacceptable, they're below 0.5, they're miserable, if they're between 0.5 and 0.59, they're mediocre if they're between 0.6 and 0.69, they're middling if they're between 0.7 and 0.79, they're meritorious if they're between 0.8 and 0.89, and they're marvelous if they're between 0.9 and 1. So you must admire the language for older statisticians. So if you were to write this up, you would say all 32 items which showed middling to meritorious adequacy for factor analysis, and you would say all MSA larger or than 0.27, larger or equal than 0.27. Okay. If some of them had not been, then you would consider removing those items. So if they're not factorable because they score really low, it basically means this item is not correlating with any other items. So it means it's noise or rubbish, and it's either you phrased it wrong or it's not capturing what you want. I'm going to do it yourself. So you can download the data from that link. The data are ratings from instructors in a study by Sedanius. Again, some type of personality ratings. I would like you to read in the data, and then you have to make, unlike our data set, it's not a clean data set, you have to make a subset with items 13 to 24, and you do that via dplyr, and if you're really clever, you can also use num range, and otherwise you're going to have to do some typing. And you can then conduct this KMO-test. So I'd like you to just do the KMO-test on the data, what we just covered. Okay, so I think this one I didn't upload in Blackboard, so you have to download it from the link in the webpage. I'm going to stop the recording for now.